Okay, hello. So this is the third part of my series of videos on simple harmonic motion. And in this one we're going to look at two real Further Maths Paper 2 exam questions. We're going to focus on approximation. So if you remember looking at the syllabus, there was this section at the bottom here. Down here, which talks about approximations. We need to recognize situations where an exact equation of motion may be approximated. So like the equation of motion, F equals ma, is exact, but it can be approximated by SHM in a certain case. And what that case is basically like this. Imagine that force is mass times acceleration, and suppose that was, for example, 7 or minus 7x plus 6x squared minus x cubed. Now this is not SHM because it doesn't follow the pattern of x double dot equals minus n squared x. But if x is small, then we can assume that x squared is very small and x cubed is even smaller. So x double dot here is approximately equal to minus 7 over m times x, this x here. So the idea is whatever formula we have for the acceleration or the force, if we can make it a linear approximation and make the force or acceleration proportional to the displacement, then we have approximate SHM. Now, what kind of approximations are we talking about? The example I give here is not realistic because you won't see an example that looks like that. So what kind of example will you see? Well, let's just try and delete that. The kind of examples you will see are listed here in the syllabus. What you're going to see is small angle approximations and binomial approximations. So let me list that now so you can see it clearly. So first of all, the small angle approximations are things that you learned in A-level maths. You learned that if theta is small and in radians, then sine theta is about theta. And tan theta, by the way, is also about theta. But we won't use that, I don't think. Now cos theta is an interesting one. Cos theta is about 1 minus theta squared over 2. But that's not a linear approximation. So in these examples, if you're going to approximate cos theta, you're going to approximate it as 1. That's important to remember. Now, the binomial approximation, if you remember from P3, is when you have cases like this, 3 plus 2x to the power maybe 7 over 2. So the important thing is this is not an integer, it's not an element of the set of integers, so for that reason you can't use the binomial theorem, you have to use the binomial approximation. Let me just move the screen a bit here. So the binomial approximation says that this can be first rewritten into the form 3 to the 7 over 2 1 plus 2x over 3 to the power 7 over 2, taking out a common factor. And then do you remember how this is written as a binomial expansion? This is written as 3 to the 7 over 2 times 1 plus n times x, where n is the power, so 7 over 2 times 2 over 3, 7 over 2 times 2 over 3 times x plus dot dot x squared, something with x squared plus something with x cubed, and it goes on to infinity. So if we're going to use a linear approximation, as we did with the angles, a linear approximation would involve cancelling. Let's just find the colour there. So cancelling all terms which are higher order than x. So the idea is x is going to be a small number. So the terms with x squared, x cubed and higher will just be ignored. So this particular example will simplify to 3 to the power 7 over 2 times 1 plus 7 over 3x. So that's what they mean by making approximations. They mean take the linear approximation so that we can get to the form of an equation which looks like this always. And I want to mention that if it's an angle, then it will be theta double dot is approximately minus n squared theta. Yeah, so we can have like an angular version of the same equation. All right, so for approximations, obviously this is approximate and not exact. Okay, that's the basic idea. Now I'm going to show you the 2 exam questions, and because they're quite long, you need the whole screen to look at them. So I'll show them. What I'll do is I'll show both of the questions right now, and you can pause the video as you choose to look at those questions. Take as long as you like to try to answer them. Either just do the first one or do both, and then come back and look at my answers. So here's the first of the 2 that I'm going to look at. That one there, yeah. So it's very big, so it's difficult to fit on the screen. First of all, notice we have the point A here, and we have a square ABCD. And here you can read the whole question if you like. This, by the way, is from Winter 2003, question paper 2. Okay, so assuming you paused it and looked at it or not, either way, I'm now going to show the second question, which is this one here. Again, it's very large. The top of the diagram has a letter C there, but apart from that you can see the whole of the rest of the question here. So again, I'll wait a moment. Okay, so those were the 2 questions. Let's first look at the first one first. Obviously, I need to just drag myself all the way down to here. Here we go. So this is the beginning of the first of those 2 questions. So quick reminder: it was Winter 2003. Obviously, question paper 2 because it's mechanics. So how do we approach this question? ABCD is a smooth, square, horizontal table. So horizontal is important because it means we're not going to consider the weight, because we're going to consider motion in a horizontal plane. Yeah. So don't make the mistake of looking at this diagram and drawing mg. Okay, the weight exists, but it's perpendicular to this diagram. So the weight is perpendicular to this diagram, and because the table is smooth, we can ignore the reaction force, and the corresponding friction force will not exist. Yeah, so mu is 0. Ignore friction, ignore gravity also. Now the center of the table is O, and there are the 2 diagonals. That's the lengths AC and BD are 4A. So OA is 2A, OB is 2A, OC is 2A, and OD is 2A. So the particle P, mass m, is resting on the table and is connected to A and to C by two light elastic strings, each having natural length A and modulus of elasticity lambda. And what we've got here is one of those horrible show questions. Yeah? Show, a very important question, very important words, telling us that we need to give good logical explanations, and in particular we need to give a diagram here. Show that when P is displaced a short distance x from O towards B, so that's what we're seeing here, P is displaced x from O towards B. The resultant force towards O is lambda x over A. If x over A squared and higher powers of x over A are neglected, so this is the idea of ax plus bx squared plus cx plus cube plus and so on ignored, only the linear part is included. Although of course there may be a constant term as well, and if there is we have to deal with that. Okay, so how should we approach this? Well, I'm going to start by drawing a diagram which is largely just a copy of this diagram. I'm going to draw the point O, maybe here, and I'm going to draw a point. What shall I call this point? A point E, and I'm going to draw a diagram showing the force. What's the best way for me to do this? Let's say that this diagram, first of all, is only considering the tension in the string AP, and then we'll generalize to the at the end. So let's say this diagram starts here, and I'll draw dotted lines. Dotted lines. So first of all, the distance from O up to A is 2A. So here's the point A, and then there's the diagonal. The diagonal here. Okay, that doesn't look right, does it? Just tidy that up a bit. Obviously, this is a lot easier with a ruler and pencil, pen. Now, I'm going to call this. I'm going to define a displacement variable x such that x is 0 at O, and x increases to the right. Yeah. So it's like drawing an x-axis going to the right. Well, that means that the distance from O to E is x. Yeah. So what we're doing here is we're considering during the motion a general point E. So why I'm writing that is the idea that P is moving. P is the particle itself with mass m, and it's moving probably backwards and forwards like this. Yeah. Well, we certainly hope so. Otherwise, this won't be an SHM question, right? So it's going to oscillate around O, and to figure out the nature of that motion, we're going to calculate the resultant force on P at a general point E, which is anywhere in the motion, here or even here. Even if it's to the left, the same thing will apply. So if it's to the left of O, then x will be negative. Okay, so I hope that's obvious. Now let's consider the force, the tension in the string AP. The tension in the string AP at E is equal, using the formula for elastic strings, lambda over natural length A times the extension of the string. Now, what's the extension of the string? Let's define this length AE as, well, we don't need to do it. Let's just say the length of the string is AE, so the extension is AE minus the natural length, which is A. Okay. Now, the tension, so by symmetry, the tension in PC is the same. The tension in PC is also lambda over A, AE minus A. Okay. And since these two forces have the same angle with the OE direction, the resultant force will simply be the components of those two tensions in the direction OE multiplied by 2. So the result, if we define this angle as theta, the resultant force in direction, let's say OD, so to the left, will be lambda. Well, let's write it in a simpler way first. 2 times TAP times the sine of theta. Okay, so that's hopefully quite simple and easy to understand. Now, sine theta is of course just x divided by 2a. So I can now write. Let's do an annotation here. I'll use a different color. So this is obviously x over 2a, while this quantity AE is obviously the square root of x squared plus 2a squared using Pythagoras. So if we want the resultant force on the particle P in the direction OD at the general point E, we simply combine these formulas into one expression. So let me just say that this line is now continuing down here, equals, so the resultant force in the direction OD is 2 times lambda over A times AE, which was the square root of x squared plus 2A all squared, minus A, because remember it's extension we want here. So that was 2 times TAP times sine of theta, which is x over 2A. Okay, let's simplify that down a bit. The 2's cancel, and I have lambda x over A squared. And inside the brackets I have, so let's just write it as 2A 1 plus x over 2A squared to the power 1/2 minus A. So just to be clear, here I'm taking out a factor 2A squared and then taking its square root. So I get, so now you can see that this expression here is of the correct form for a binomial expansion. 1 plus x to the power n equals 1 plus nx plus n minus 1 over 2 x squared plus and so on, the binomial expansion, yeah? So what we're doing is we're just because we see this square root term and this is not linear, so we're going to have to approximate it to a linear function by using the binomial expansion. So let's continue to do that. Here we have an A and an A, so that cancels with this A, giving lambda x over A. And here we have 2 times the binomial expansion of this, which is 1 plus nx, where n is 1/2, so that's x squared over 8a squared plus ... I don't need to write the rest of the binomial expansion, minus 1. And here's an interesting point, is that we want to ignore, according to the question, terms with x over a squared or higher. Yeah. So x over a, the idea is that x is much smaller than a. If x is much smaller than a, this number is much less than 1, which means its square is very, very small, and the same with its cube, and so on and so on. So making this, ignoring this, gives us force towards O, force in direction from O to D is approximately, here we're approximating lambda x over A 2, and we're ignoring the x squared term minus 1, which is lambda x over A, which was required by the question. Okay, so that's how we demonstrate this. Now this example is a little unusual in terms of the binomial expansion, and the reason for that is that we're actually ignoring the second term. So we're not just ignoring here terms in x squared, we're also ignoring terms in x, and the reason for that is that our x in this binomial expansion, you can see, is actually the square of something already. So it's as if we're writing 1 plus x to the power n is approximately equal to 1. Now that might look stupid, but the terms of the question are that we must ignore terms with x squared and higher, so that's why this term here is getting ignored, and we're just getting lambda x over a. So I hope that's pretty clear, although it is a bit unusual, as I say. Okay, let's look at the second part of the question. It says 2 additional strings, PB and PD, are now introduced so that P is connected to all 4 corners of the table by strings of length natural A and modulus of elasticity lambda. So the 4 strings are identical. The particle is displaced from O a short distance towards B. Well, that's the same as before, and is released from rest, and we need to show that we're getting SHM. So this is also a show, so again we need to be careful to draw a nice diagram, clearly define our variables and all that stuff. Okay, first let's consider forces so I'm going to draw all four forces. First of all, there's TAP, then there's TCP or PC, which we drew in the previous diagram. But now there will be two additional forces, one towards B, so TBP, and one towards, oops, wrong way around, TBP in this direction and TDP in that direction. So there's now going to be four forces to deal with. Of course, the good news is we already know the effect of two of the forces because that's what we calculated in the first part. But in order to show the SHM clearly, I'm going to again want to draw a clear diagram of displacement. So here's O with a line there, and along this line, somewhere at the end of this line, I'm going to have the point B, and somewhere at the end of this line, I'm going to have the point D. So they should be the same length. So this should be 2A, if we remember, and this should also be 2A. Now I'll mark on also the natural lengths of the strings between D and P and B and P. So using a different colour, I could mark on the natural length A of the left-hand string and the natural length A of the right-hand string. You don't really need to draw this much detail, but it can help if you're trying to learn. Now, just as before, we need to consider what's happening in a general position, some particular position like this one here, some point E. So this is the point E here, or, well, maybe that's not so helpful. Some general point here, E, and as before, I'm going to define my displacement variable x so that it is 0 here, and I'm going to draw, I'm going to have x being more and more positive to the right, okay, so that I can be really clear about my signs, because it is easy to get confused about signs in these questions. Now, in order to calculate the resultant force, I'm going to calculate the resultant force on the particle. So let's be really clear. Resultant force on particle P at a point E, distance x to the right of O. So in other words, at E the value of x is x, if that makes any sense. Okay, and I'm going to, so what would that be? Well, first of all, I'm going to, well, yeah, I should write what it is exactly. It is exactly equal to TBP, which is a positive force, so that, yeah, so here T, if we look on the diagram on the left, TBP is pointing to the right, so it's a positive force because x is positive to the right, whereas TDP is to the left, so we should subtract that force. Now the effect of TA and TAP and TCP is only approximate, so actually I can't use an equals sign here. I need to say it's approximately. It's approximately equal to those two, which are exact, plus the effect of TAP and TCP, but we just calculated that the effect of TAP and TCP is approximately a force lambda x over A to the left, so that needs therefore to be subtracted, lambda x over A. Okay, so to complete this we need to include the formulas for the tensions TBP and TDP. So let's consider TBP first. Extension of BP at the point E. Well, if this is x, and we know this is 2A, and we know the natural length is A, so the extension is the distance from here to this point here. So that's just A minus x. Yeah. So if, for example, if I call this F, EF is OF minus OE. OF is equal to A and OE is equal to X. So the extension of BP is at E is A minus X. The extension of DP, the string on the left, at E, well, that's also easy because this is A, so if this is point G, GO is A, and then we have X, so that's A plus X. So then, therefore, it's easy to calculate the values of TBP, lambda over A minus X, and TDP is lambda over A plus X, and then we have the approximation for the effect of AP and CP as lambda X over A. So therefore the resultant force can be approximated. So you see this cancels with this A term cancels with this A term, so I get minus lambda X over A, minus lambda X over A, minus lambda X over A, or minus 3 lambda X over A. That's the approximate value of the resultant force on P at a point E, which is at a distance x to the right of O. So I'm being really clear here, you see, about how I'm doing my working. Okay, now I need to show that I've got approximate simple harmonic motion. So obviously if this is the force, then m times x double dot, where x is the displacement variable we gave here, is approximately equal to minus 3 over a times x, or let's just say x double dot is equal to minus 3 lambda over ma times x. So this is SHM by definition. Center of the SHM is O, because when x is 0 we're at O. And the last thing we need to do is just to find the period of this motion. So period can always be found very easily from this basic equation. It's just 2 pi over the value of the constant n, and the constant n is the square root of 3 lambda over ma. So tidying that up a little bit, I've got 2 root ma over 3 lambda times pi. So that's the end of the question. So what to say about this question? I would not consider it a very difficult one, but I would not be surprised at all if you were confused about exactly how to go about this section here. Yeah. The reason it's strange is because you're approximating 1 plus x to the n, but you're actually taking out all the terms in the expansion except the first one, just the 1. Okay. Now the second part is a standard SHM proof. It's a little bit more complicated than normal because we have 4 tension forces, but the difficult part was already done in part 1. So I hope that makes sense to you. I'm now going to go on to the second question. In case you've forgotten what it was, I'll just show it to you again. There it is. You can pause if you like and look at it. The point up here is the point C. So that's the whole question. I should say, if you want to try to do this and you haven't studied rotation, in particular if you haven't studied the idea of moment of inertia and torque, then you might find this question a bit difficult. You can do it without that knowledge, it's just a bit less obvious. And either way, whether you've studied it or not, you may still find this question quite difficult. I know that the examiners said in their report from 2007 winter exam that very few students were able to solve this correctly. So it's a challenge, and if you find it difficult, fine. Try to follow my answer, and I hope you'll all the more the case that you'll learn something from it in that case. So let's have a look now at my answer. Okay, starting here. The first problem with questions like this is understanding the physical setup. So physically, what have we got? We've got a light rod. That means the mass is 0. That means the rod AB has no mass, so we can forget about its weight. It doesn't have any. Its length is 2a. It's freely jointed at A. What does that mean? This is something you should have learned in the context of rigid bodies in equilibrium. Freely jointed means you have some kind of hinge here. You could almost imagine like AB is the door of a room. It's so A can move and can pivot around the point A. So AB can rotate with center of rotation A, and there is no resistance to that rotation at A. There's no friction forces. By the way, that does not mean that there's no contact force at A. There certainly is, but that won't be important in this question. Alright, so that's A, freely jointed at A. A particle mass m is attached to B, so that means at B we do have a weight force mg. Now, a light elastic string, so it's an elastic string, natural length A, modulus kmg, has one end attached to B and the other end attached to C, where C is fixed vertically above A. That's how I know that this is the vertical direction, because C is vertically above A, distance 2A. Now the system is in motion in a vertical plane without the string becoming slack. Why does it say in a vertical plane? Well, CA is vertical, so we imagine B rotating backwards and forwards, up and down, as like on this picture, but there is no motion into the screen or out of the screen. Yeah, so it's motion all in one plane, a vertical plane. The string does not become slack. What does that mean? Well, it means that, if this is the natural length A of the string, it means that as B moves backwards and forwards, it doesn't move so far that we lose tension in the string. So there will be tension in the string all the time, all the way through the motion. Okay, so just a few notes there on the physical setup. So already, if you've understood so far, you should already imagine or visualize that if I pull B down a little bit and release, it's probably going to bounce backwards and forwards in some kind of oscillation motion. And because A is fixed, B will actually be moving along a circular arc, won't it? B is constrained to move in such a way that the length AB is fixed at 2A, which is another way of saying circular motion. Okay, we're going to show something. Now this is a little bit scary. It looks a bit complicated, but it's not so uncommon on further maths to have formulas like this. So how are we going to show this? We're going to start using Newton's second law as it applies to rotation. And this is something you should have learned in the last topic in further mechanics. If you haven't yet learned it, it is still possible to do the question, but I won't talk too much about this because I think this is the easiest way to do the question. And how do we understand this? Well, torque is the turning effect of the forces. I, the moment of inertia, is the resistance to rotation, and theta double dot is the angular acceleration. So we're going to be calculating, we're going to be finding a formula for the angular acceleration of the particle B. Oh, well, I don't really need to say that, do I? Of the system, yeah, about with a pivot at A. So first of all, what's I? I is the moment of inertia of the system AB. Yeah, the physical system here is AB, but the only place where there's any mass here is at B. Okay, so AB has no mass and no weight, but at B there is weight. So the moment of inertia about A is the moment of inertia of the single particle at B. And if you know basic moment of inertia, you know that it's mass times distance squared. So here the distance is 2A, the distance from the pivot squared, so that's 4ma squared. So the moment of inertia is 4ma squared. So we need to figure out the torque. Now the torque is the net moment about A. So first of all, what is the turning effect, the moment clockwise moment due to the weight, due to the particle, do I call it particle or just a particle? So what's the turning effect of this weight force around the pivot A? Well, we see that this angle here is theta, so the perpendicular distance of the line of action of this force from the pivot A is just 2a sine theta. So we want the weight mg times the distance 2a sine theta. Now what's the moment which is anti-clockwise due to the tension force? That's the other force acting on the system. There's only two forces, yeah? Sorry, that's not true. There is a contact force at A, but if we take A as the pivot, there's only two forces which have a non-zero turning effect about that pivot. There's T and there's mg. So to find the anti-clockwise moment due to the tension force, we need to find the perpendicular distance. Let me try and draw this as best as I can. Whoops. The perpendicular distance of the line of action of the tension force from the pivot A. So that's this distance here, and we already know this angle because this is 2a and this is 2a, so this is an isosceles triangle, so this is half the angle. This is theta over 2. Now you could draw this on a separate diagram on your answer. I'm just cheating and drawing on the question paper here. Okay, so the moment due to the tension force is easy to calculate. It's the tension force itself multiplied by this distance. Let's call this point x, ax, and ax is 2a cosine theta over 2. Okay, so the net torque. Now we should be careful here when we refer back to the equation of motion, the equation of rotational motion. When theta increases on this diagram, you see that theta is increased when we have a clockwise rotation, which means that the clockwise turning effect is positive, and the anti-clockwise turning effect is negative. So theta increasing corresponds to clockwise rotation. Therefore, the correct sign for the torque is it's the clockwise rotation minus the anti-clockwise rotation. So it's 2mga sine theta minus 2ta cosine theta over 2. Okay, so the next thing we have to do to solve this problem is to find the formula, the correct formula for the tension force. Now this is an elastic string BC, so the tension force is equal to lambda E over L, where lambda is modulus elasticity, E is extension, and L is natural length. So let's refer back to the question. The natural length of the string is A, the modulus of elasticity is kmg, so we can write this as equal to kmg over A times the extension. Now the extension is the difference between the length BC and the natural length A. So that's BC minus A. So we need to do a little bit of thinking here. What is BC? Well, BC is simple trigonometry. Bx is 2a sine theta over 2, and I have to multiply that by 2. So I get kmg over A times 4a sine theta over 2, and then subtract A. Okay, so finally I'm getting the full formula for the torque is 2mga sine theta minus 2 times A times cosine theta over 2 times my formula for tension, which was kmg over A 4a sine theta over 2, and then minus A in the bracket there. But we know that torque is equal to I theta double dot, and we said I was 4ma squared theta double dot. So we see finally we have a complicated but correct equation, I hope, for the angular acceleration. We just need to rearrange this equation. So first of all, what common factors can we cancel? So we can cancel 2, we can cancel m, we can cancel a. So let me put theta double dot on the left hand side. Cancelling 2ma gives me 2a theta double dot on the left hand side, and on the right hand side 2ma cancels. I get g sine theta, and I'm cancelling this a and this a cancels here, but I've also got another a here and an m and a 2, so I've got something like minus kg cosine theta over 2, and then in brackets 4 sine theta over 2 minus 1. Okay, nearly there. So theta double dot, taking out common factor g, dividing by 2a, I've got sine theta, took out the g, so I've got 4k cos theta over 2 sine theta over 2, and then I've got plus k cos theta over 2. Okay, so now we recognize that using the formula sine 2 theta equals 2 sine theta cos theta, so I can simplify that middle term, and I get theta double dot equals g over 2a sine theta minus 2k sine theta plus k cos theta over 2. So just for completeness, let's make the exact form in the question. K cos theta over 2 minus 2k minus 1 sine theta. And that was to be shown. Okay. So obviously that's quite a long, complicated bit of algebra. So I don't blame you if you found that a bit hard. Patience is important. You probably can't do it as quickly as I just did it because I'd already practiced it before. So do take your time. You have a good, I don't know really, I suppose a good 10 minutes to do that in the exam. Maybe even more than 10 minutes. Maybe you have 12, 13 minutes. So there's no need to rush. But of course, because it's a show question, you have to be very clear. So we've proved that this formula for the angular acceleration is correct. Now let's see what the last part of the question. In the equilibrium position, theta is pi over 3. Find the value of k. Well, equilibrium is another way of saying zero net force or net torque and zero net angular acceleration. So if angular acceleration is 0, that means this factor here is 0. So I can equate k cos theta over 2 to k cos theta over 2 is the same as 2k minus 1 sine theta. So if theta is pi over 3, that gives me k cos pi over 6 equals 2k minus 1 sine pi over 3. Well, cos pi over 6 and sine pi over 3 are the same, so I've got k equals 1. So that's nice and simple. I've got k equals 1. Now it says by substituting theta equals pi over 3 plus epsilon, where epsilon is small, show that the motion is approximately simple harmonic and give the period. So yet again we're being asked to show SHM. But it's an approximate SHM. And let's get a picture here of what we're saying. We're saying that we know that when the angle theta is pi over 3, we have equilibrium. This is an equilibrium position. And they're saying suppose theta is pi over 3 plus epsilon, where epsilon is small. So this is some very small angle, hopefully, epsilon. What they're basically saying is if we displace the particle, pull the rod downwards by that much, and release, we're going to get an oscillation which is a simple harmonic oscillation with respect to the angle theta. And the way to prove this is the way exactly the same as we did with the linear cases. We just have to use an approximation which is linear and then rewrite the formula for the acceleration, prove that it's proportional to the displacement, except the displacement here is an angle displacement. So okay, let's substitute, because they told us to do it, let's substitute pi over 3 plus epsilon for theta in the original formula, which I'm going to copy down here. G over 2a k cos theta over 2 minus 2k minus 1 sine theta. So we're going to let theta be pi over 3 plus epsilon. We're going to get angular acceleration is g over 2a. Now k is 1, so that's 1 times the cosine of theta, which is pi over 3 plus epsilon divided by 2, minus 2k minus 1, so k is 1, so that's 1 again, sine of this angle theta being pi over 3 plus epsilon. So as we visualized here, epsilon is very small, it's close to 0. So what does this give us? Let's continue down here. So therefore, theta double dot, we're going to need to use compound angle formulas to simplify this out, aren't we? So cosine A plus B is cosine A cosine B. Let's just write this down. Cos A plus B, cos A cos B, minus sine A sine B. Hopefully you know that, because I suppose if you don't, you're kind of in trouble doing further maths. Yeah. So here I've got cos pi over 6 cos epsilon minus sine pi over 6 sine epsilon over 2, over 2 there, because it's epsilon over 2. Okay, and then minus sine A plus B, that's minus sine A cos B minus cos A sine B, so minus sine pi over 3 cos epsilon, so here it's actually epsilon, not epsilon over 2, minus cos pi over 3 sine epsilon. Okay, so it looks very long, but we're going to be able to use approximations. So epsilon is small tells me that sine epsilon is approximately the same as epsilon, and cos epsilon conveniently is approximately the same as 1, and that will be true for any small value of epsilon. So therefore I can write now an approximate form. Theta double dot is g over 2a, right, cos pi over 6 is root 3 over 2, cos epsilon over 2 is just 1 in approximation form, sine pi over 6 is a half, sine epsilon over 2 is epsilon over 2 approximately. Now sine pi over 3 is root 3 over 2, cos epsilon is about 1, cos pi over 3 is 1 over 2, sine epsilon is about epsilon. So we've actually used these, approximations in 4 distinct positions here to get what we need. But it's all based on epsilon being a very small angle in radians. So here we can see some cancellation. Let's just mark that off. And the terms in epsilon do not cancel but add together, and I'm getting minus epsilon over 4 minus epsilon over 3, so that's minus 3 epsilon over 4. So finally we have what we need, more or less. We have theta double dot is approximately equal to minus 3g over 8a times epsilon. Okay, nearly finished. This is not quite an SHM equation because the variables are not the same, are they? Theta and epsilon are not the same. But just as we've discussed in the previous 2 videos, because the difference between them is only a constant, they have the same second derivative. Yeah. So because let's say, which way around do I want to do this? Yeah, epsilon is theta minus pi over 3. It follows that epsilon double dot, the second derivative of epsilon with respect to t, is the second derivative of theta with respect to t minus 0, let's say, because this has 0 second derivative. Okay, so they have the same second derivative, so we can finally say that epsilon double dot is approximately equal to minus 3g over 8a epsilon, which is SHM with center. What's the center position? When epsilon equals 0 and theta is equal to pi over 3, which is the equilibrium position. Yeah. Now what's the period? Same as before, the period is 2 pi over the number n, which in this case is the square root of 3g over 8a. So therefore the period is 2 root 8a over 3g multiplied by pi. And you notice in these questions they often don't bother to give you specific numbers, you just write the formula. Okay, so that would be the period of that oscillation. I hope that was clear. I know it was quite a hard question, so don't feel upset if you can't answer it easily. But there are many other examples to try of a similar type over the last 10 years of past papers. Okay, so that's pretty much everything I wanted to say about SHM. There are other cases I could discuss, but obviously there's a limit in terms of time. Now, I'm not sure when I'll do it, but I probably will do some more further maths videos, further mechanics videos, in particular about rotation, about the topics of moment of inertia and rotational dynamics. So I'll leave that for now. Thank you very much.